All right. So before we get going on lecture 31, which is on something called parametric surfaces, I kind of want to summarize lecture 30, because I think that was definitely a hard lesson. And I think we may have lost the forest for the trees in that one. I think we may have kind of lost sight of what we were trying to do with that. So the theme of last lesson is that Green's theorem is nice. So let me kind of write this at the top margin here. So Green's theorem is a smiley face. Now, why is that? It's because we can turn either a really difficult line integral into an easier double integral, or as we saw near the end of class, we can turn a double integral into a line integral. And especially if we end up having a conservative vector field, it's going to end up giving us 0. So Green's theorem is like, if you can use Green's theorem, it's usually a good idea to do so. And that was kind of theme of the lecture quiz as well. Rather than doing things directly, like following along a triangle, for example, like doing 3 different parameterizations, we should use Green's theorem instead and then do a very easy double integral just once. So the theme of last lesson, if you got kind of lost in the details, is that Green's theorem is nice. So I just wanted to say that before we move on. All right, anyways, lecture 31, what are we going to talk about today? Today we're going to talk about parametric surfaces. So far we've talked about parametric equations or parametric curves. So back before calculus 2, every curve we saw kind of looked like this, or maybe like this. Like for example, a circle, the unit circle would have this form. So this is how we used to see curves. And then at the end of calculus 2, we learned about parametric equations. It's kind of funny because I'm actually going to give this lecture today in Calc 2. But we saw that x can be a function of t, and then y can be a function of t right here. Now, what about surfaces? So we originally saw surfaces as z is a function of x and y, although sometimes we can mix all of the variables together. Like for example, a sphere of radius, say, I don't know, 2 would be something like this. Now, it turns out that there's a way to parameterize surfaces as well. And why would we want to do that? Well, we used parametric equations to be able to do these line integrals, right? So we're able to do these line integrals right here, and we were able to follow along a curve in space. What we're going to do in the next lesson here is we're going to do something kind of similar to line integrals, where we're going to integrate a function along a surface that's not necessarily just the xy plane or something like that. So we're going to kind of bump up line integrals a dimension from line integrals to being called what are known as surface integrals. But before we do that, we need to know how to use parametric equations to define a surface. All right, so that's why we're having today's lesson here. All right, so to describe a surface, 2 independent variables u and v are now required for each of the component functions. So why do we need 2 variables? Well, it turns out that surfaces are 2-dimensional. I think that's a fact that everyone kind of realized, and curves are 1-dimensional. But what does this really mean? You can think of the dimension as the minimum number of variables or coordinates required to uniquely identify a point on whatever space you are. So since we're 2-dimensional, we need 2 parameters, u and v, and they also have different names too. We need 2 variables to define everything going on our surface here. All right, so let's look at the formal definition. So let x, y, and z be functions of u and v that are continuous on a domain D right here. And D is where u and v live here. The set of points x, y, z given by this position vector, which depends on on u and v. We have our function for our x coordinate, our function for our y coordinate, and our function for our z coordinate. Kind of like how we had a function for each coordinate up here, we also have a function for each coordinate down here. And this is going to be a parametric surface when we have 2 variables right here. All right. So let's go ahead and see some examples of this. Let's see how we can parameterize surfaces. So our first example will be relatively simple here. We're going to parameterize the plane through the point 2, 4, 7 and parallel to the vectors 1, 0, 3, and 278. Okay, what's going on with this? Well, let's just say for a moment that this is the point 247. Maybe this vector right here is 278. And then let's say this one maybe is 103. This probably isn't drawn to scale based on these proportions here, but let's just say this is what's going on. Then our plane will be this right here. We want to find a parametric equation or parameterization for this plane right here. Okay, now how are we going to do that? Well, we need to come up with a function, a vector or a vector R that will depend on u and v. Okay, well, let's see here. Let's think carefully about this. So we know we want to include the point 247 in our plane, right? So it makes sense that we should probably put 2, 4, and 7 right here. Now, remember back in Calc 2 when we were first parameterizing lines, like we were finding the parametric equation for a line? The way we did that was we included the point that the line goes through as a constant, kind of like what we did here. And then we had the direction in which the line was going as a vector times, I guess, t, usually in that case. But in this way, in this situation, we have two different directions we can go. We could either go this way, we can go across this way, or we could go up diagonally this way by following this vector. So it's almost like we have just two different direction vectors for our plane here. So what we're going to do is we're going to stick a variable next to each one of them. So I'm going to do u times this one and v times this one. For those of you who have taken linear algebra before, this is a linear combination of these two vectors. We're taking any possible linear combination. Don't worry if you don't know what that means, though. All right, so we have u times this, the x component. And then we have v times the x component here, so times 2v. Here we don't have a u component, so it's going to be 0 times u, so this doesn't really influence the y direction, whereas this will be 7v. And then finally, we have 3u for our z, and then we have 8v right here. Now, what this does is this allows us to plug in any combination we want of u and v, and we can get to any point on this plane that we desire. So I just want you to kind of see the parallel between this and making a parametric equation for a line. We have our constants here, and then we have our directions times the variable right here. Okay, so that's parameterizing a plane, and we can use the same kind of formula to parameterize any plane we like. Let's move on and let's talk about using the angles theta and phi from spherical coordinates. We want to find a way to parameterize the unit sphere centered at the origin here. All right, well, let's see here. Oh, is this similar to the previous unit where we made equations out of vectors? I guess it's kind of that way. We're making equations out of two variables, which are called parameters. So we take as input these parameters. We need two of them because surfaces are two-dimensional. And then we get as an output a vector that points to different points on that surface right here. All right, so let's go ahead and parameterize the unit sphere. Now, spherical coordinates, what are those? Well, remember the conversions for spherical coordinates. X, we have rho sine of phi cosine of theta. Y is rho sine of phi sine of theta. And z is rho cosine of phi. All right, now we're the unit sphere, correct? So this means that all of our rows will be 1. So we have sine of phi here times cosine of theta. We have sine of phi times sine of theta. And then we have z is cosine of phi here. And lo and behold, we've managed to express x, y, and z in terms of theta and phi. So there is our parameterization for our surface. So a vector that will point to any place we want on the unit sphere could be defined like this: sine of phi, cosine of theta, sine of phi, sine of theta, and cosine of phi. So there we go. We found our parameterization for our unit sphere or unit ball, if you like. All right. So that's spherical coordinates to help us get a parameterization. Let's go ahead and see if we can use cylindrical coordinates to help us do the same thing right here. Why is it still u and v? Because I made a mistake. It should be phi and theta. Thank you. Yeah, u and v are kind of just the generic terms, although sometimes we'll have differences in those, like for the angles right here. All right, so we're going to use cylindrical coordinates to find a parameterization of the cone. Z is root x squared plus y squared, and z is limited to being between 0 and 5. All right, now first of all, let's turn this formula into a formula involving cylindrical coordinates. So x squared plus y squared is r squared, and we have the square root of r squared, which will be r, since I guess we're assuming r is positive here. All right. So let's see here. So we know z is r. Now in cylindrical coordinates, we know that x is r cosine of theta, right? And then y will be r sine of theta. Now, using this equation here, we could also write z in terms of r, and I guess technically theta, even though it's not there. We have z equals r right here. So that means that we could write the surface with only needing two variables. So our r, and this is going to be a little bit stupid, but we have r of r and theta. This is what's called in mathematics, and I guess also physics as well, an abuse of notation. Because technically I should pick a different variable because I already used r for this. But I think it's pretty clear that these are different because we have the vector symbol over this one, and we have the letter here for that. So this is what's known as abusive notation, where we overload the same variable, but we still know what it means. So our x coordinate is r cosine of theta, our y is r sine of theta, and according to the cone, z is equal to r. Okay, now because we have this limitation on z right here, we need to make a limitation on our theta and r. So since z is equal to r and z needs to be between 0 and 5, well, I guess that means that r needs to be between 0 and 5 as well. All right, now what about theta? What are our traditional limitations for theta? Yeah, we're just going to do 0 to 2 pi. All right. So in addition to specifying the equation for our surface, we also need to specify any restrictions on our variables. All right, let's move on to the next one here. Here we have a cylinder, x squared plus y squared equals 9. And again, we're limiting this to z being between 0 and 5 right here. All right, so let's see here. X squared plus y squared, this is r squared is 9. So since I guess in this class we're using positive r values, r is going to equal 3 here. All right, so we want to parameterize x and y, right? So let's see here. Let's see if we can come up with that. So we have r. This time we're just going to use theta and z. Okay, so we know that since x squared plus y squared is 9, we know that r has to be 3. So if we have x is r cosine of theta right here, well, in this case, x needs to be 3 cosine of theta. And y is r sine of theta, well, then that means that y will be 3 sine of theta for this example. And then we're just going to have z be, well, z. Z is technically a cylindrical coordinate, so we can use it here. Now, once again, we do need to specify our limitations on our variables because we at least have this one. And then, which kind of comes part and parcel with cylindrical coordinates, we have the restriction on theta. All right, so there we go. So there's our parameterization of this surface. And again, we're only using 2 variables right here. Isn't this parameterizing line integrals in 3D? Yeah, so essentially we're bumping up parameterization by a dimension. So previously we already knew how to parameterize curves. Now we're learning how to parameterize surfaces. And next class, when we previously knew how to do line integrals, we will now learn how to do something called surface integrals, but we'll save that for lesson 32. How do you know to use cylindrical and not spherical? Well, they told us to do it in this example. Could we use spherical for this? In general, I always have the bias where I only use spherical if it's an actual sphere. Otherwise, I try to use cylindrical coordinates. All right, let's move on to this final example here. Let's do the cylinder, and the only difference between this cylinder and that one is that we're shifting our center of our cylinder here. So we're shifting it center to be 0, 3 rather than 0, 0. Okay, well, and that means we should have a similar parameterization, but it might be a bit different here. Let's see. So they did nothing to change the x. So I'm not going to change the x. I will do something to change the y, though. What do you think I should do to change the y? Right here, to reflect that we are now centering this at y equals 3. Yep, that's right. We're just going to add 3 to it. Yeah, so we have 3 sine of theta plus 3. All right, that's good. And then, well, we could have z equals z again. And just as before, we have our restrictions on z, and we have our restrictions on theta. I suppose if I was being more rigorous, I should have also put restrictions on the example on the previous page here. So for this one, we know that phi is limited to being between 0 and pi, and theta is being between 0 and 2 pi. So I guess I should have specified that back here. I didn't need that for the plane, though. T can be any value. T and S can be any value whatsoever. All right. Let's see. How do we know to use R and theta versus theta and Z? Oh, it just depends on the type of equation you were given. So for this first one, since Z was equal to R, there was no point in having a Z variable here because we could just use R. And we already knew we were going to use R and theta for X and Y here. So that kind of encouraged us to use R and theta. Whereas with these two equations here, they don't give a Z at all. So we should probably have that in there somewhere. And because of these, we know our R has to be a very specific value. Our R is going to be 3 right here. So it's kind of just whatever works best for each situation. All right, I think I'm mixing up the notes that I wrote myself earlier and the ones I'm using. But whatever. All right. So let's see here. Normal vectors and tangent planes. So remember earlier in the course, when we had a surface, we were often tasked with finding a tangent plane to that surface at a particular point. Now with parameterizing surfaces, we can still do this. But what we're going to do is we're going to do it a little bit differently. So suppose S is a parametric surface given by these equations here. So U and V will be our variables. So this is over an open region such that X, Y, and Z, so these functions of U and V, have continuous partial derivatives on D. And remember, D in this context for this lesson is going to be from 0, it's going to be the place where U and V live. Sorry, I got distracted for a second. So this is where U and V live right here. Okay, now we have the partial derivatives of R, and these are going to be defined as, you could probably guess how these are going to be defined. We do the R derivative or the derivative of R with respect to U. That's just doing the U partial derivative of all of our coordinates here. So we have partial X, partial U, partial Y, partial U, and partial Z, partial U. And then now we can really guess what R sub V is going to be. So we take all the V derivatives of this. Now, how do we interpret each one of these? This you can imagine this is the rate of change of R, the vector, in the direction of U, or I guess I should say or, V. So for example, if we want to change what the U parameter is doing, that's definitely going to affect what our vector is pointing towards. So this will tell us how much that is going to move right here. All right. So yeah, and here's a picture kind of explaining what's going on with this. I'm not a huge fan of this picture, to be honest, because it shows u and v going in the same directions as y and x, but that's purely a coincidence. U and v need to have nothing nice to do with y and x. Like potentially u could go maybe in this direction, maybe, and then v could be like going over this way. So u and v don't have to be in the same direction as y and x. This is a frowny face picture. It's not giving the whole story here. So u and v technically don't have to be nice with respect to x and y right here. But what is nice about this picture is that the vectors here are kind of giving what's going on here. So if this is the u direction, if we move this way, then this vector is telling us what's happening to our position vector, which direction that's moving as we move in the u direction. And then the same for v right here. Okay, now we have this normal vector that's pointing directly out of our surface right here. Now, earlier we had a way of finding the normal vector. We found it through the gradient. But we're actually going to have another way of finding the normal vector now. If we look at what RU and RV are doing, if we take the cross product of these, then we will be perpendicular to our surface, because these are technically going in the direction of the surface at this very point. So if I take the cross product of these, then I will get my n here. So another way of finding a normal vector is to cross RU and RV right here, because U and V are the two different directions that we can go on the surface. So if we're perpendicular to both of them, then we need to be perpendicular to the surface itself. Moral of what I just said is a way of finding the normal vector is RU cross RV. And of course, we could do it the other way as well. It's just the normal vector would point downwards instead. All right, and if the normal vector is not 0, then the surface is going to be called smooth. So some of our theorems in the near future are going to be referring to this, this smooth property here. And we'll see why not being 0 is important. All right, so let's use this newfound knowledge in a parameterization of this paraboloid to help us find a tangent plane. So find an equation of the tangent plane to the paraboloid. R of uv is uv u squared plus v squared at the point 1, 2, 5. And remember, these are x, y, and z values here. So here's our point 1, 2, 5. It's on our paraboloid. We want to find a tangent plane there. Now, they didn't give us the xy equation for this. They instead gave us the parametric or the parameterization for this surface. All right, well, let's go ahead and figure out what our RU and RV are, because if we cross those, then we'll have a normal vector. And remember, normal vector is the key to finding the equation for a tangent plane. So let's figure out what RU is. Let's do that first. Let's see, I do the u derivative of u, I'm going to get 1. I do the u derivative of v, I get 0. And I do the u derivative of this, and I have 2u. All right, let's do RV now. So I do the v derivative of u, and I get 0. I do the v derivative of v, and I get 1. And then I do the v derivative of this right here, and I have 2v. Okay, now we want these to be specific numbers, right? Because we want to have a specific tangent plane. But how do we know what u and v are at this point? Well, remember, x is equal to 1, so that means that this component needs to be 1. Y is equal to 2, so this component has to be 2. And then z has to be 5, so this component's got to be 5. And thankfully, they just had single variables right here, so this immediately tells us that u is 1 and v is 2. And that also satisfies this last equation as well. Okay, so that means that our RU is really going to be 1, 0, 2. And our RV will be 0, 1, and 4. Okay, now a normal vector for this plane can be found by crossing RU and RV. So let's go ahead and do that. Let's dust off our cross product skills here. 1, 0, 2. And then we have 0, 1, and 4 right here. All right, let's go ahead and do a cross product. So we do the cross product here. What's our I component? Well, we do this times this minus this times this. So that's going to be -2. For J, we have this times this, so 1 or 4, and then we subtract 0. But remember, J gives us an extra negative sign, so we have -4. And then finally with K, we do 1 times 1 is 1, and we subtract 0. So this ends up being a normal vector for our tangent plane. Okay, now let's dust off our memories of this as well. How do we assemble our tangent plane once we have a normal vector? Well, remember what we do is we dot the normal vector with, how do we used to write this? R minus R naught. And that's got to be 0. All right, so what does this mean? So I take the normal vector, -2, -4, and 1, and I dot this with x minus the x value of the point, so x minus 1, y minus the y value at the specific point, so 2, and then we have z minus 5. And all of these have to, oops, not dot 0, all these have to equal 0 here. And remember, why is this? It's because this is the normal vector to this plane, or this vector in the plane. This vector is in the plane, and this is normal to it. So if you have two things that are perpendicular and you dot them, you get 0. That's why this is equal to 0 right here. All right, so let's see here. Let's go ahead and dot. So we have -2 times x minus 1. We have -4 times y minus 2. And then we have 1 times z minus 5, 0. And this seems to me an acceptable form for our tangent plane right here. All right, I feel like we're preparing for an Avengers level math crossover event. Yeah, it is kind of easy to forget with all these details, like what we're doing this for. We'll definitely show you some examples once we kind of get everything assembled in this section here. Then we'll show you some applications. All right. Now, let's say we wanted to find the area of a parametric surface. And this is going to lead us into next lesson, which is going to be talking about what are known as surface integrals. All right. So what we're going to do is we're going to approximate the area of a parametric surface using a Riemann sum. All right. So I want you guys to ignore this picture again. I think this picture is a little bit misleading here. It kind of gives you the impression like, oh, I just multiply these two and that's going to be my area for here, which it's not quite what we're doing with this. What we're trying to do is we're trying to find the area of each of these little, what I like to think of it as scales, or you could also think of them as mini planes. What we're doing is we're trying to find the area of all these scales or mini planes. And where do these come from? Well, we go a tiny bit of a direction in the v direction, the way the v is changing. And then we go a tiny bit in the u direction where u is changing. And so we're going to try to find the area of this mini plane right here. Now, another thing that's a bit misleading about this picture, this shows that u and v are kind of nicely perpendicular to one another. But remember, u and v don't need to be like that. They don't need to be like a nice checkerboard like this. It's not necessarily that way. Because if we go back to something we did earlier, remember our very first example, if we find RU and RV, they're going to be these vectors here, and these are definitely not perpendicular to one another. So I want to emphasize this picture is a bit misleading. It's showing these coordinates as perpendicular when it's not really the case. All right, so what we're going to do is we're going to find the area of this little plane right here. All right, so this little plane is going to be called, the area of it at least, is going to be called delta Sij. All right, so the area of delta Sij is the area of a parallelogram determined by these vectors. So we go a tiny distance in the RU direction, and we go a tiny distance in the RV direction. Now we're trying to find the area of a parallelogram made by these two vectors. Does anyone recall a way of doing that with vectors? How did we do that? We did the cross product. That's right. So if we want to find the area of the parallelogram made by these vectors here, which I emphasize again, it could very well look something like this. Like this could be our V, this could be our U right here. So it could very well be something like that. Then we're going to take the cross product of them. So we have delta UI R sub U cross delta VJ R sub V. Okay, so what we're going to do is we're going to pull out the delta UI and the delta VJ because those are constants. And then we're left with, oh, I guess the equals, I was going to do that down here. We have delta UI, delta VJ. And then we have magnitude of RU cross RV, or our normal vector from earlier. This interpretation is going to be important next lesson. All right, so this is what we're trying to find. This is going to be the area of this little scale right here. And as you might expect, as we make these scales smaller and smaller, and as we have more of them, the little part where they're kind of departing from the surface right here is also getting smaller. So our area for our total surface is getting smaller and smaller, or our error for it is getting smaller, until finally, when these are infinitely small, we have infinitely many of them, we get the exact area for this whole thing right here. Okay, so what is this saying here? So if each point on the surface corresponds to exactly one point in the domain D, and I emphasize again, this is where U and V are, not X, Y, then the surface area is this right here. So we have the integral over the surface, and we're adding together all these little scales or mini planes. And the area for each of those is defined to be this right here. And I'm going to call this dA now. All right, this is going to be dA in the UV world, in D right here. So if we ever want to find the surface area, what we need to do is we need to parameterize our surface, or if we're already given one, that's nice. And then we just do the double integral of the cross product, or the magnitude of the cross product of these right here, because that's going to be the size of all these little parallelograms that we have, which could very well look like this. I don't like that all these pictures have these nice squares right here. They could very well look like this. And this will be illuminated a bit more in an example that we're going to do. Okay. Now let's suppose that we had, before we do the example though, let's suppose that we have our surface given in a more traditional way. So let's say we have Z, and I don't know why this is K here. I'm just going to call this F. Let's say that Z is a function F of X and Y right here. So we can parameterize the surface using R of X and Y. And how can we do that? Well, the X coordinate will be X, the Y coordinate will be Y, and then Z, the Z coordinate will be this function of X and Y. So if we have our surface written in the traditional way right here, then we could write our vector pointing to it like this. So this is the X coordinate, the Y coordinate, and the Z coordinate. All right, so if we try to do the thing that we did on the previous page right here, well, I think I have some people getting a little bit confused about what we're doing with this. So I want to go back over here. So this is just a surface, right? This is a two-dimensional object. So we can find an area associated with this. And if we were in a previous lesson, we might try to find the volume underneath this, but we're not trying to do that right now. All we're trying to do is we're trying to find the surface of this thing, or the area of this surface right here. So you can imagine this is kind of like a blanket that someone wiggled around a bit, and it's kind of floating up there. And we want to find the area of that right here. And then, yeah, Tristan has a good summary. It's just a 2D object in 3D space. That's exactly what it is right here. Okay, now let's suppose that this surface, so let's go back to this picture. Let's suppose this surface had a nice traditional formula where we have Z on one side and then all the X's and Y's on the other. Then there's actually going to be a simpler formula for the surface area for this. So here's our parameterization using X, Y, and Z. So now our Rx will be, well, the X derivative of this is 1. The X derivative of this is 0. And then we have partial F, partial X. The y derivative goes much the same way. We have 0 for this, 1 for this, and then we have partial f, partial y right here. Okay, now let's go ahead and do the cross product of these right here. So if we do the cross product, this is this determinant, 1, 0, partial f, partial x, 0, 1, partial f, partial y. Let's see. For the I component, we do this times this minus this times this. So we have negative partial f, partial x. For j, we have this times this minus this times this. That's going to be, and then we have the extra negative. So it's going to give us that. And then for k, we have 1 times 1 minus 0 times 0. So that's actually just going to be 1, no matter what, right here. All right. So there we go. So we have this as our cross product. Now the magnitude of this cross product is the square root, and then we square each of the components and add them together. So we have partial f, partial x squared, and then we have partial f, partial y squared, and then we have 1. So in summary, if we have a nice traditional formula, an explicit formula where we have z as a function of x and y, then the surface area integral for that is going to be the double integral of the square root of partial f, partial x squared, partial f, partial y squared, plus 1. So we could just do this integral instead if, I emphasize the if we already have z as a function of x and y right here. All right, enough about the theory though. Let's go ahead and actually use this to find a surface area. And I want to draw a picture, and I think it'll make the derivation of that formula look a bit more understandable here. All right, find the surface area of the unit sphere. So we have, and then they give us our parameterization of the unit sphere right here. Okay, well, the surface area is going to be the double integral over d, where d is the domain of phi and theta. And then we're going to have the magnitude of r phi cross r theta. And then maybe we'll have d phi, d theta, or something like that. All right. So let's figure out what r phi and r theta are first. We'll cross them and then find the magnitude. All right, r phi. Let's see. I do the phi derivative of this. I get cosine of phi, cosine of theta. I do the phi derivative of this. I get cosine of phi, sine of theta. And I do the phi derivative of this. I get negative sine of phi. Next, let's compute r theta right here. Let's see. So I do the theta derivative of this, and I have negative sine of phi, sine of theta. Do the theta derivative here, and I get this. And then I do the theta derivative of this, and I get 0. Okay, now it is time to cross these vectors right here. And then there's going to be a lot of trig identities that we're going to use, and it's going to boil down to something really nice. It'll be very easy to do this integral once we're simplified. So let's write in all the components here. Cosine of phi, sine of theta, negative sine of phi, sine of phi, sine of theta, sine of phi, cosine of theta, and 0. Okay, so let's see here. With I, the I component, we're doing this times 0, and then we subtract this times this. Now, subtracting that negative will make it all positive. So we're going to end up with sine squared of phi cosine of theta. All right, next let's move on to our j component. We have this times 0, which is again 0. And then we have this times this, but we're subtracting it, but it's the j, and then we have 2 negatives already. So there's 4 negatives involved with that, which washes out to be a positive. So we have sine squared of phi, sine of theta for that. All right, I ran out of room on this line. Let's see. And then K, we have cosine of phi cosine of theta times sine of phi cosine of theta. All right, so that's going to be sine of phi cosine squared of theta. And then I'm going to, what am I going to do? I'm going to subtract these two multiplied together. So I'm subtracting a negative, so I'm going to add. And then we see our first nice event happen. So I have this times cosine squared, and then I have this times sine squared, meaning I can rewrite this sine squared of phi cosine of theta, sine squared of phi sine of theta. And then, since this is a Pythagorean pair right here, this is just sine of phi cosine of phi. All right. Now remember, we don't want necessarily just the cross product. We want the magnitude of the cross product. So let's go ahead and do that. What does the K component say? It's sine of phi cosine of phi. And back here we had that, but it was part of a Pythagorean pair. So we have cosine squared and then sine squared right here. All right. So let's see. So the magnitude of this, all right, so we have the square root and then all of these squared. So we have sine to the fourth of phi cosine squared of theta. We have sine to the fourth of phi sine squared of theta. And then we have sine squared of phi cosine squared of phi. All right, well, if we see our second Pythagorean pair right here, we have cosine squared and sine squared. So this will just turn into a sine to the fourth of phi plus sine squared of phi cosine squared of phi. All right, and then we could factor out a sine squared from in here, and furthermore, we can remove it from the square root. So the square root of sine squared will be positive sine of phi because phi is in between 0 and pi. So this will be positive anyway, so it doesn't need an absolute value. And then we have sine squared of phi. I pulled a sine squared out of that, so it's just cosine squared of phi. And there is our third Pythagorean triple. So as promised, this boiled down to something really nice. All of that is just going to be sine of phi right here. So this is what we're going to integrate over the range of our parameters here. So the range of our parameters, as I just said, phi goes from 0 to pi, and theta goes from 0 to 2 pi. So we're going to do our double integral of sine of phi d theta. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. All right, now this is an integral we can use the multiplication trick on. So this is 0 to 2 pi of d theta and 0 to pi of sine of phi d phi. Oops, that's a phi. There we go. All right, so this we've seen a million times. This is going to be 2 pi. The integral of this will be negative cosine of phi from 0 to pi. When I plug pi into here, I have negative 1, which will be 1. And then I subtract negative 1. So this is a fancy way of writing 2. So we have 2 pi times 2, and just as we ran out of space, we found that the surface area is going to be 4 pi right here. So this is how we can use a surface integral to do the integral of this. Now you might be wondering, okay, why wasn't, based on the picture back here, based on the kind of bad picture that I crossed out earlier, you might expect me to just do the integral of d phi times d theta, right? If we just put a d phi d theta in there, that's dA. And if I add all those together, I'm going to get the area. Why isn't that just going to be the area? Why do we need this sine of phi in there? And the answer is that if we parameterize this according to phi and theta, you've actually seen this parameterization before. I guarantee you've seen this because I guarantee that pretty much all of you have seen a globe before. So if you've seen a globe, you know that there's kind of like the coordinates going over it, right? Like, so we have the lines denoting longitude and latitude. So if we have our sphere, we have these longitude lines here, well, as best as I can draw them. And then we have our latitude lines going like this. Okay, now let me ask you this. If we go up here where the lines start to get kind of crunched together and we fill in one of these, this is a du times a dv. This is a du times a dv, but it's really close to one of the poles. And then I shade in this one right here. And this is also a du times dv. It's the same thing. But you notice that these are vastly different areas right here. And this phi right here, the phi value of this block is close to pi over 2, and sine of pi over 2 is 1. And this phi has a value that's close to 0, and sine of 0 is 0 right here. So this is the picture that I want you guys to focus on when we're thinking about surface area right here. Not all of these delta U, delta V boxes are created equal. Some of them are very tiny, and some of them are much bigger here. That's why we need to compute R phi cross R theta to get the relative size right here. All right, so let's see. All right, well, actually, it looks like we finished a few minutes early here. So anyways, this is going to be our building block for the next section where we're going to do something called surface integrals, which are kind of like line integrals, only we're bumping it up a dimension right here. All right, anyways, that's it for today. So I will see you guys on Friday where we will do measure set.